Again, quick safeguarding message. If you're under 18, please inform a parent or guardian that you will be in this meeting. During the meeting, cameras and microphones should be switched off as the meeting will be recorded. If you have any questions, you can instead use the Google Meet chat. I'll try and respond as quickly as I can. After the meeting, I'll post a solution to any unfinished questions in the tutor announcements channel. We're going to be going over the four specification points shown here. Newton's first law, Newton's second law, Newton's third law, and moments, with a particular emphasis on smooth pulleys and connected particles. Alright, so to start with, some mechanics terminology. In general, mechanics words tend to be the extreme versions of regular words. It's like light doesn't just mean lightweight, it means there's literally no mass. So equilibrium means not moving or rotating. A particle means the size of the object or the shape of it can be ignored. Rough means there is friction. Smooth means there is no friction. Tension, we'll go on to that in a bit, but it means the force in an extended rope or string. And uniform means that all of the mass is assumed to be in the middle. Exam questions will use these words, so they're very important to learn. Alright, to start with, Newton's first law states that an object at rest stays at rest unless a resultant force acts upon it. Equivalently, an object in motion stays in motion unless a resultant force acts on it. So what this means is that in order for an object to accelerate or to change velocity, there has to be a resultant force that isn't zero. So as an example, a planet drifting in deep space, since it's far away from everything, there'll be no gravitational forces acting on it, and so it will remain in motion. Newton's second law is probably the more useful of the three. F is equal to ma, where the resultant force is F, the mass is m, and a is the acceleration. So the force put onto an object is equal to the mass of the object times the acceleration it experiences. So as an example, a force of 100 newtons acting on a 50 kilogram object will accelerate at 2 meters a second squared, because 100 newtons is equal to 50 kilograms times 2 meters a second squared. Newton's third law. Forces go in pairs, with each being equal and opposite to each other. Example, if you exert a force of 50 newtons onto a wall, the wall will push back at a force of 50 newtons on you, which is the cause of a normal contact force. This law is especially useful for questions that ask to find the force that one object exerts on another object, as the force that A exerts on B will always be equal to the force that B exerts on A, and sometimes this is easier to calculate. Alright, so I've got some example questions. Question 1. An astronaut weighs 735 newtons on Earth and 120 newtons on the Moon. Calculate the acceleration due to gravity on the Moon. Right. From here, we can start by using Newton's second law, F equals ma. We know that on Earth there is a force of 735 newtons, and this will be equal to the mass times the acceleration on Earth, which we know is 9.8. From here, we can then work out the mass, which will be 735 divided by 9.8, which is 75 kilograms. So that's the mass of the astronaut we now know. We can then look at the moon section, where we can use F equals ma again. We know that the force on the moon is 120 newtons, and this will be equal to our mass times the acceleration due to gravity on the moon, which is what we're trying to calculate. Rearranging, we get that the acceleration is equal to 120 divided by 75, which if you put that into a calculator is 1.6. So our final answer is 1.6 meters a second squared. Comparing that with the mark scheme, we calculated the mass of 75, then we calculated acceleration of 1.6. Right, we've got a second exam question over here. A particle of mass 5 kilograms is on a smooth inclined surface at 30 degrees. There tends to be a lot of questions about inclined surfaces. Calculate the acceleration down the slope. So for this one, we have our inclined surface with an angle of 30 degrees. And we have our object of 5 kilograms. This will be pulled down due to gravity. And since F equals ma, the force of gravity is equal to the mass times the acceleration of gravity, which is g. So in this case, we have force is 5 kilograms times the acceleration of gravity. So we have a force 5g downwards. I'll write that on the left. Right. Then there is also the normal contact force due to Newton's third law, since it's applying a force onto the surface, so the surface will apply a force onto it at 90 degrees. Now, since it's the normal contact force, we have to find the component of this 5g's of force that is perpendicular to the surface, which will look like that. To find this distance, we can use some trigonometry. We know that this angle is 30 degrees, which means that this angle is 60 degrees, which means that this angle is 30 degrees, which means that this side length is 5g cos 30. In general, the way to remember when it's cosine and sine, cosine is always when you're sort of moving through the angle. If you imagine like a rod at the 5g force, if you're moving it over to the smaller side length here, you're going through the 30 degrees. So it's got to be 5g cos 30. And likewise, the other one, you know that this angle is 60 degrees. So this will be 5g cos 60. Right, this is getting a bit messy, but we do now have all the forces labelled. This is 5g cos 30. Our normal reaction force is equal and opposite, so this will also be 5g cos 30. Our resultant force is equal to the sum of all the forces. We know that this force up here and the 5g cos 30 down here are going to cancel out since they're equal and opposite. So the only force we have to consider is this 5g cos 60. If you put this into a calculator, you should get 4.9 times, wait no, sorry. You should get 5 times 4.9. You can then use Newton's second law, and F equals ma. We know our resultant force. We know our mass is 5 kilograms. A is equal to, this side length would be 5g cos 60. You could also write it as 5g sin 30. Just to answer the question in chat. Oh, someone's requesting to join. One sec. Alright, we then know that the acceleration must be... That's excellent. The acceleration must be the force divided by the mass, which is 5 times 4.9 divided by 5, which is equal to 4.9 meters per second squared. These diagrams do tend to get a bit busy, but over time you learn to simplify it down and not have to write down as much. It takes a lot of practice. Comparing this to the Marxian, you indeed get a half of gravity, which is equal to 4.9. Right, going back to the slides. Right, next up is connected particles. When two particles are connected, we know that their accelerations must be the same. The force in a rope that keeps the particles moving at the same acceleration is called a tension. You can visualize it as there being as a rope pulling on each object. Okay, got another example question here. So over here, the tension of a rope is pulling the 4 kilogram mass this way and pulling the 6 kilogram mass this way. Well, the force we'll label T for now. Okay, to find the acceleration of the particles, we know that each particle must have the same acceleration, and so we can consider the total acceleration. So the total acceleration times the mass will be equal to the total force due to F equals ma. Our total force is 20 newtons plus 100 newtons. Our total mass is 6 kilograms plus 4 kilograms, which is 10 kilograms. And our acceleration is what we're trying to work out. So we then have 120 is equal to 10a. Therefore, a must be equal to 12 meters a second squared. That's part A done. Then part B is to work out the tension in the rope. Here what we can do is we can pick a weight, say the 6 kilogram one, and consider only the forces acting on that weight. So here we have the tension force acting to the right, 20 newtons to the right. We know it's accelerating at 12 meters a second squared, and so we can use F equals ma again. So our force is 20 newtons plus T. Our mass is 6 kilograms. And our acceleration is what we calculated in part A. So we know it's 12 meters a second squared. As such, T is equal to 72 minus 20, which is 52 newtons. That's the tension in the rope. Bring up the Marxian again. Total force is 120 newtons. Total mass is 10 kilograms. Acceleration is 12 meters a second squared. And tension is 52. Right, there are various types of connected particles. The most common one is ropes and strings. As said before, they have equal acceleration, but only when the string is in tension, meaning it's like pulled apart by the objects. So in the previous example, this 4 kilogram mass was moving faster than a 6 kilogram mass, which is causing the rope to be stretched out, which is why we could assume that their accelerations are the same. If a 4 kilogram mass was instead moving towards the 6 kilogram mass, then the rope would buckle and we could no longer assume the same acceleration on both masses. That differs to rods, where no matter which way they're moving, they both can have equal acceleration. Lifts is when one object is like either on top of or to the side of the other. In that case, they're only going to have equal acceleration, and one of them is pushing on the other, so moving towards it. And finally, pulleys are like strings, except the accelerations of the two objects, they'll be the same magnitude of acceleration, but they'll have different directions. I've got some more practice questions here. I've got 3 of them of varying difficulty. Right. This one has a lot of words, but it also has a nice diagram to help us. The light scale pan is attached to a vertical, light, inextensible string. So here, light means mass is 0. Inextensible means you cannot extend it. The scale pan carries 2 masses, A and B. The mass of A is 500 grams. And the mass of B is 600 grams. A rests on top of B as shown in the diagram. The scale pan is raised vertically using the string with an acceleration of 0.5 meters per second squared. So in diagrams, it is common to see acceleration labelled as a double arrow. Right, part A, calculate the tension in the string. Right, it might be more useful to draw our own diagram. We have the string here with some tension upwards. We have a scale pan. We've got a mass with 600 grams of weight, which is equal to 0.6 kilograms. We then have another mass on top. That is 0.5 kilograms. Right, it's asking us to find the tension in the string. So for this, we can recognize that there's going to be a downward force due to gravity of 0.6 g from this object, and another downward force due to gravity of 0.5 g due to this object. We know that the string is being held up, so this upwards force must exactly counterbalance these 2 downwards forces. So this upwards force is 0.5 g plus 0.6 g, which is 1.1 g, which, if you put that into your calculator, get 10.8 newtons. Alright, part B asks us to find the force exerted on mass B by mass A. I don't know if I was clear on this last time, but this is a great example of Newton's third law, since we can swap mass B and mass A, since we know that the force on mass B by mass A must be equal to the force on mass A but by mass B. So what we can do is consider only the forces on mass A. This has the effect of essentially zooming in on this block here. We know it has that downwards force, 0.5 g. got the normal reactive force, which is the value we're trying to calculate, and it is accelerating upwards at, what was it, 0.5 meters per second squared. Alright, we can then use F equals ma again. You know, our net force is going to be our normal reactive force minus 0.5g. It's got normal reactive force going up, 0.5g going down. This will be equal to our mass of 0.5 kilograms times our acceleration of 0.5 kilograms. We can then solve this equation to get our normal reactive force is equal to 0.25 plus 0.5g, which is equal to 5.15 newtons. Since this is the normal reactive force of B onto A, this will then be equal to the force on mass B by mass A, due to Newton's third law. So that is question B done. Alright, question C. I'm going to move this question down so we can see it a bit better. Find the force exerted on mass B by the scale pan. Right, here we can do the same trick as last time. We can find the force on the scale pan by mass B. So drawing our scale pan, you know it's got an upwards force of 10.8 newtons. And we know it's got a downwards force due to the contact force. From B. The question says that the scale pan is light, so we don't need to consider its weight. As such, we can use F equals ma again. We know the total force is 10.8 minus our contact force from B. I'll label it C for now. That is going to equal the total mass of everything on the scale pan. So we have a 500 gram mass and a 600 gram mass. So this is going to be a 1.1 kilogram weight, mass even. And then we have an acceleration, as stated in the question, of 0.5 meters per second squared. From here, we can rearrange to find C equals 1.1 times 0.5 minus, oh, one sec, it was the wrong way around. C is equal to 10.8 minus 1.1 times 0.5. Which is equal to 10.25. So our contact force of B onto our scale pan is 10.25 newtons, which means that the force on B by the scale pan is also 10.25 newtons. So we've answered the question. Alright, I recognise I've been going through this quite quickly. Does anyone have any questions for now? You can send it in chat if you do have any questions. Hang here for like a few seconds, then I'll move on. Right, go to the next question then. Oh wait, we do have a question. So we always convert to kilograms. Yes. If you do the force in grams, then you won't get. So if you do the mass in grams, then you won't get the force in newtons. You'll get the force in millinewtons. And in general, it's a lot easier to just convert to kilograms. Alright. So we've got another practice question here. Hopefully. Oh no, it's crashing again. Ah, there we go. I'll put this back. Particles P and Q of masses 2m and 3m are attached to the ends of a string that is modelled as light and inextensible. The string passes over a small, smooth, fixed pulley, and the masses hang with the string taut. So we should start by drawing a diagram of this, because this is, again, a lot of words. So we have a particle P and Q of masses 2m and 3m. They're attached to the ends of a string, which is light and inextensible. So string has no mass. The string passes over a small, smooth, fixed pulley. So a pulley, we'll draw that as a circle. And the masses hang with the string taut. Right, so if we imagine these two masses hanging, one sec, let's draw that a bit bigger. So we have a pulley with 3m mass right and the 2m mass on the left. And the masses hang with a string taut. Okay, question A is to find the acceleration of each mass. So there are two main methods, one of which is more reliable than the other, so I'll start with that. You know that the tension in a string is pulling them together. The tension is going to be that way. We then know that these two masses each have a weight of 2m, their weight, times gravity. This one will have 3mg. Alright. This force is then tension. And we know that there's going to be some acceleration up. Call this A. And that will be equal to the acceleration down here. So if this particle is accelerating upwards, that means this one must be accelerating downwards. So then, considering just the 2m mass, we can use F equals ma. The total force, let's say upwards, is going to be T, our tension, minus 2mg, which will be equal to the mass, 2, times the acceleration, which we don't know. Then we can do the same thing for the 3m mass. Our force, which this time will go downwards, so our force is 3mg minus T. Which will be equal to our mass, 3, times our acceleration. And from here, we now have simultaneous equations in terms of T and A. To solve this, we can add the first equation to the second equation. So the T's are going to cancel out. 3mg minus 2mg is going to give mg. then 2a plus 3a is going to give 5a. And therefore a is equal to a fifth of mg. So a quick question, why is the force mg and not just g? That's because in the question it says that the masses are 2m and 3m rather than 2 and 3. If the mass was just 2, then it wouldn't be 2g. But since we're multiplying the mass by m, we also multiply the force by m to get to mg. Right? Alright, back down here. Now that we know a, we can plug this back into the first equation. Our tension minus 2mg is equal to 2/5 mg, since that's 2 times a. From here, T is equal to 2/5 plus 2 mg, which, if I put that in the calculator again, that is 2.4, that times 9.8 is 23.5 m. Since the question doesn't tell us what m is, we leave our answer in terms of m. Alright, so question A is asking us to find the acceleration, which is 1/5 of mg. Question B is asking us to find the tension, which we've done here. It's 23.5 m. Question C, find the force exerted on the pulley by the string. Our diagram is getting a little bit far away here, so I'm going to see if I can copy it over. Interesting. Never mind, it doesn't like me, so I'll just draw it again. Alright. Question C is asking us to find the force exerted on the pulley by the string. Now, based on Newton's third law, we know that this is equal to the force exerted on the string by the pulley. So we have this upwards force, which is our normal contact force. We have these two downwards forces from earlier. And we know that the whole thing isn't like falling. Since it says that the pulley is fixed, we know that this remains in place, and as such this system must be in equilibrium. So you can say that the net force is equal to 0. But we can also calculate the net force using our normal contact force minus 2mg minus 3mg. That also gives us a net force, so this must be equal to 0. Therefore, our normal contact force is equal to 5mg, which, if you substitute g as 9.8, put that in your calculator, get 49 m. Again, since the masses are in terms of m, we're fine to leave our answer in terms of m. And as question D, criticize the model. This, you can really pick just about anything. I'm going to go for the string is unlikely to have 0 mass. Now, it's one of the assumptions we made at the start. and is fairly unrealistic since all strings have some mass. Right, we've got 17 more minutes, it should be fine. This is our third and final practice question for connected particles. Right, a block of... That's not meant to say woods. Oh, I see. A block of wood A of mass 0. Hang on a sec. Yeah, a block of wood A of mass 0.5 kilograms rests on a rough horizontal table and is attached to one end of a light inextensible string. So we'll draw the diagram as we go here. Got a block A, mass 0.5, rests on a rough horizontal table. Rough means there's going to be friction involved. Does everyone here know how to deal with friction? Just to check. Right, yeah, I'll simplify it for now. I'll save it as smooth. Just because we're focusing on the connected particles. Right. A block of wood A of mass 0.5 kilograms rests on a smooth horizontal table and is attached to one end of a light inextensible string. The string then passes over a small, smooth... That's meant to say pulley. You can tell I'm really good at typing. A small, smooth pulley P fixed at the edge of the table. The other end of a string is attached to a ball B of mass 0.8 kilograms, which hangs below the pulley. The resistance to motion of A from a rough table, again, I'm simplifying it as smooth table, has a constant magnitude F. The system is released from rest with the string taut. After release, B accelerates downwards at 3.2 meters a second squared. We have a downwards acceleration of 3.2 meters per second squared. Since it is going over a pulley, the acceleration up here will be to the right instead. Alright, question A, calculate the tension of the string. Since the string got the tension always going inwards. Alright, from here, we can use F equals ma on block A. So we have the net force, which is equal to our tension, is equal to our mass, which is 0.5, times our acceleration of 3.2. As such, the tension is equal to 1.6. Alright, question B. Show that F, what was F? Oh, F was the, right, yeah, F is the friction, so that'll be for another time. Right now we're just focusing on connected particles and we're about to go into moments. Alright, before I go into moments, just another check. Is everyone alright with connected particles? I know that last question was a bit botched, but okay. So moments. A moment is a rotational force. It can either be clockwise or anti-clockwise. To calculate a moment, you can use moment is equal to the perpendicular force times the distance from a pivot. If the force is not perpendicular, you should find the perpendicular component and ignore the parallel component. I'll show you what I mean in a sec. So here we have a lever. This triangle in the middle is our pivot point. We've got a mass on the left pulling down at 10 newtons, 2 meters away from the pivot. So our moment is going to be 10 times 2 to give 20 newton meters anti-clockwise. Over on the right, we have a non-perpendicular force. So we have to find the perpendicular component, which in this case will be 5 newtons times cosine of 60 degrees. We then multiply that by the distance to get a total moment of 15 newton meters clockwise. The moment from this mass is 15 newton meters. The total moment will be 20 newton meters anti-clockwise minus 15 newtons clockwise, giving us 5 newton meters anti-clockwise. Alright, before we do some practice questions, some useful information. Equilibrium always means the resultant force is 0 and the resultant moment is 0, no matter what point you choose as your pivot. This is also referred to as at rest. Since it doesn't matter what the pivot is, the resultant moment is always 0, you essentially can choose which pivot to take moments about, which you can use to simplify your calculations. For example, if you have an unknown force, it's a good idea to have the pivot be about that point, since the distance to the pivot will be 0 and that will cancel out the unknown force. If an object is uniform, you can assume all of its weight is directly in the middle. If a system is at the point of tilting, then the normal reaction force at the pivot is 0. That one's a bit more complicated. We'll get into an example later. Alright, starting with example question. Right, the following diagram shows a system of weights on a rod in equilibrium. Calculate the normal reaction force at C and D. So you know that these masses will have weight going down. Hang on a sec. Oh, sorry. Got the wrong numbers on this diagram. We've got a force going down of 3G, force going down of 10G, and a force going down of 6G. Then at C and D, it's also going to be a normal contact force going up. We'll call this one C and this one D. Alright, since the system is in equilibrium, the moment about any pivot will be 0. So it's useful to choose our pivot as C, because then we don't have to consider what the force of C is. Right. So total moment. We'll start with the moment from this one. This is an anti-clockwise moment, and it's going to be equal to 3G, which is the force, times 1 meter, which is the distance. Since it's anti-clockwise, we'll write it as negative. Here, we then have a 10 kilogram mass producing a force of 10 Gs, 2 meters away from the pivot. So we have a clockwise moment of 100 G. Oh, sorry, of 200. 20 G. Because that is our 10 G, which is our force, times our distance of 2 meters. Alright, we then have the normal contact force at D at a distance of 4 meters. The force is D, the distance is 4. This one is going counterclockwise, so it'll be negative. And finally, we have a force of 6 Gs going down, so this will be a clockwise force, and it's at a distance of 5.5 meters. So 5.5 times 6 is 33. Since the system is in equilibrium, we know that the total moment is going to be equal to 0. And so we can then rearrange and simplify. So minus 3g plus 20g plus 33g is going to be equal to 50g. And we'll move the 4d over to the right. And therefore d is equal to 50 on 4g, which is equal to 122.5 newtons. Alright, so we've now worked out what D is. Of course, we also want to work out what C is. So this time we're going to find the total moments, but with D as our pivot. So we have a 3 kilogram mass producing 3 Gs of force. There's going to be an anti-clockwise moment. This time it's at a distance of 5 meters and a force of 3 Gs. So it'll be negative 15 Gs moment. Then we have the force of C, a distance of 4 meters. We have a force of 10 G, a distance of 2 meters. We don't need to consider D, since it has a distance of 0 meters. And finally, we have a clockwise moment of 6 Gs times 1.5 meters. Since it is in equilibrium, no matter where we put the pivot, the total moment is going to be 0. As such, we can then solve for C. Now we have minus 15 Gs, minus 20 G, plus 9G, which is going to be, one sec, I'm going to put that in the calculator. That's going to be minus 26G equals 0. Thus, 4C is equal to 26G. And C is equal to 26 on 4G. That is 63.7 newtons. And with that, we have completed the question. This is our normal contact force of D. This is our normal contact force at C. Alright, the same system. What's that? Yeah, no, it's just actually crashed. Sorry about that. Alright, the same system as last question has an extra weight added on top of the 6 kilogram weight. The system is now at the point of tilting about D. So I only briefly went over this earlier. But the point of tilting means that the moment about D is equal to 0, and if you were to add more weight to this side, then it would cause the whole system to rotate. So what we do, right, yeah, at the point of turning, the normal contact force is always 0. So in this case, when we have our C force, C is going to equal 0 when we take pivots around D. We can then use that fact and construct another resultant moment equation. About point D. So we have a 3 kilogram mass causing 3 Gs of force 5 meters away from D. It's going counterclockwise, so it'll be negative 15 Gs of moment. We then have this 10 kilogram one. We can ignore C since it's 0. This is producing 10 Gs of force 2 meters away from D. We then have this stack of 6 kilograms and m kilograms, causing 6 plus m Gs of force down, 1.5 meters away. This one's going clockwise, so it'll be positive. And the resultant moment must be 0. Alright, from here we can rearrange again. What I'll do to make it easier, I'll divide both sides by G. Then I'll move 15 and 20 to the right. Then I'll divide both sides by 1.5. I'll just write it as a fraction. So m is equal to 35 over 1.5 minus 6, which is equal to 17.3 kilograms. And yep, that is all the time we have available today. I'll send the feedback form link in chat. This is my first time tutoring, so I'd really appreciate it if some people could fill that out. But yeah, thank you for your time. If there's any questions, I'll stay around for a few minutes to answer them. But for now, you're free to leave.